Okay, so good afternoon. This is the second lightning talk session, and I think we are running 15 minutes over time, so I have to enforce strictly time limitations. 4 minutes for everybody. First speaker is Javid Naikoo, University of Warsaw, multiparameter parameter estimation perspective on non-Hermitian sensing. Please, Javid.
Yeah, thanks. Thank you. So I'll be talking about this multi-parameter perspective on non-Hermitian sensing, which is essentially about uh, exploiting the non-Hermitian properties of non-Hermitian Hamiltonians that govern the physical systems to do some impressive quantum metrological tasks like parameter estimation. This work is in collaboration with Janik Kolodensky of University of Warsaw and Rabindra Chachlani of Adam Mickiewicz University, Poznan. So, quick recap of non-Hermitian Hamiltonians. If you have a system that has a net gain, one can describe it by Hamiltonian H1, where the parameter B plays the role of a gain parameter, a gain rate. Similarly, if you have a system with a net loss, you can describe it by Hamiltonian H2, where this parameter B now plays the role of a loss gain loss rate, sorry. And if you allow for coupling between these two systems, you can have the equilibrium situation if this coupling strength dominates the gain and loss rate, and you can describe the system by Hamiltonian H3. The eigenvalues for this Hamiltonian turn out to be E plus minus, and the corresponding eigenvectors are given by psi plus minus. Interestingly, when this loss and gain rate equals the coupling strength, you have the two eigenvalues becoming degenerate, and not only that, but the corresponding eigenvectors also merge at this point, and the system essentially loses its dimensionality. We call such points as exceptional points, a term that I'm going to use often in the coming few slides. Sorry. So what makes non-Hermitian systems better sensors? Well, if you have a Hamiltonian H naught with the corresponding eigenvalue omega naught pertaining to the eigenstate psi given by equation 1, and you now perturb this Hamiltonian by parameter theta with a perturbing Hamiltonian H1, then you can write an expansion for this omega in terms of this parameter theta around omega naught by equation 3. However, if the Hamiltonian H naught is non-Hermitian in the first place and bears an exceptional point, which is this point of degeneracy of eigenvalues and eigenvectors, and the order of this exceptional point is n, which means that n levelers get merged at this point. Then you can expand this omega in terms of what is called a Newton-Poisson expansion. And now for small theta, if you restrict it to the first terms in theta, you clearly see that theta to the power 1 over n dominates in comparison to theta. So what it tells you is that non-Hermitian systems respond drastically to the external perturbations in comparison to the Hermitian counterparts. That's what makes them better sensors. Here is the actual model that we consider. It consists of two cavities bearing modes A1 and A2 with the corresponding frequencies omega 1 and omega 2. The two cavities are connected to baths characterized by operators B1 and B2, and then one probes these two cavities using these probe channels characterized by operators A1 and A2. Using the input-output formalism, one can actually decompose these fields in terms of the input and outgoing fields. The probe channels use the Gaussian fields to probe these modes A1 and A2, and we know the Gaussian fields can be completely described in terms of the amplitude, which I call mu here in equation 5. Mu in represents the input amplitude, and mu out represents the output amplitude. Similarly, the letter V represents the covariance matrix, where in and out stand for the input and output covariance matrices respectively. Note that the output amplitude and covariance matrix are completely described by the response function G, which is defined in equation 7 in terms of M, which is nothing but the Hamiltonian written in the quadrature basis.
You are at 4 minutes,
Now that we have
30
this,
seconds.
yeah. Any questions?
Please wrap up in
Yeah.
30 seconds.
Yeah. So the point is that one can perturb this system by in different ways depending on the form of this Ni, and correspondingly talk about the sensitivity, which is nothing but the variation of the standard deviation in this parameter with respect to this parameter itself. So it was pointed out recently that one can have quadratic scaling in such systems, and what and this scaling was attributed to the exceptional points. What we found in this study is that the exceptional pointers do not play any crucial role. It is essentially the singularity of the underlying Hamiltonian that is doing the whole magic, and one can end up with different scaling depending on the form of the perturbation in the system, and the heterodyne measurement provides the optimal measurement strategy for such system. Thank you.
Thank you very much. So we are almost at 6
Any
minutes.
questions?
Yeah, I'm afraid we won't allow for questions now. Thank you very much, Javid. And let's move on to the second speaker, Ákos Budai. So both Javid and Ákos chose not to use the webcam because they are using their mobile phone to connect. So Ákos is from Budapest University of Technology and Economics, and he will talk about cheap readout error mitigation on expensive NISQ computers. Ákos, could you please share your slide? Looks good. Unmute yourself, please, and go ahead. You are muted now.
Hello. Can you see my laser pointer as well?
Yes, it works.
Okay. So, hello everyone. My name is Ákos Budai. I'm from the Budapest University of Technology and Economics, and the title of my talk is Cheap Readout Error Mitigation on Expensive NISQ Devices. This is a project in collaboration with András Pályi and Zoltán Cimborás. NISQ is an acronym for Noisy Intermediate Scale Quantum Computers, so the kind of quantum computers that are already available today. And this talk is going to be about the financial aspects of running quantum algorithms on these devices. For example, Amazon, through Amazon Bracket, provides access to the ion trap computers of IonQ and the superconducting computers of Rigetti. But in order to run algorithms on these computers, you have to pay money on a shot-by-shot basis. So the amount of money you need to pay grows with the number of circuits that you run. So we can think of a situation where we have a quantum task that we want to solve, and we have a certain amount of money allocated that we can use. And since there are also errors present in these NISQ computers, we should also consider doing some error characterization task to get meaningful results. Then it becomes an optimization task between the quantum task that we want to solve and the error characterization task. So let's consider a simple problem where this situation comes up. Our quantum task in this simple model is a single qubit, single parameter estimation task, where the state of the qubit is IP, square root of p times 0 plus square root of 1 minus p times 1. And what we want to do is to estimate this parameter p. So naturally what we would do in this case is to prepare the state many times and qt times, and then measure it. And based on the proportion of results, proportion of times we measure 0 or 1, we would get an estimate. But we know that we also have the readout errors present. So in this minimal model, we also consider a readout error. In this situation, we consider a symmetric bit flip readout error with this error parameter alpha. So the probability of measuring 0 is not exactly p, but 1 minus alpha times we actually measure the state incorrectly. So so we want to estimate this parameter alpha, and in order to estimate it, we measure the state 0 and X times, and we get an estimate for alpha, but we also use some prior knowledge that we can have about the value of alpha. So we do a Bayesian analysis. For example, we depict here a prior probability density function for alpha, such that alpha is somewhere between 0 and 0.1. We don't know where, but we know that it's not higher than that. And so after doing the quantum task and the readout error characterization task, we get an estimate for P. This estimate has a mean squared error, or we can call it shot noise. That depends on the two shot numbers introduced on the previous slide, and also on the readout error prior width. The optimal shot numbers for the two tasks are the ones that minimize the mean squared error of the estimate. So in this slide, we show analytical approximate results for the optimal shot numbers in case of a scenario where the total shot number is fixed. On the x-axis here, we can see the width of the readout error prior, which we call mu alpha. And on the y-axis, we have the total shot number, n sub s. And the color plot shows the optimal number of shots that we should use for the readout error characterization task divided by the total shot number. We can distinguish clearly between two regions in this plot. On the lower left, the optimum is at 0, while on the upper right, it's at non-zero values. So there is a clear boundary between the two regions, and that's the main point that I wanted to say. So thank you for listening.
Thank you very much. We have 1 minute. So maybe there's no question in the chat, so I can maybe ask a question. So how can you characterize this prior distribution of your readout error? Do you have any tools for that, or how do you get your information about that prior?
So for example, we could have earlier measurement results of these parameters alpha. So for example, using calibration data of the providers themselves give us.
Great, thank you very much. Thank you, Ákos, for the nice talk. And let's move on. The third speaker of the session is Vadym Kovtoniuk. Vadym, are you ready to share your screen? So Vadym is from Taras Shevchenko National University of Kyiv. Title is Generalized CHSH Inequalities for Hybrid Measurement Schemes. Vadym, can you share your screen?
Okay, so can you see my screen?
It's coming. Yes, it's great. It's perfect.
Okay, so let me firstly explain what hybrid measurement scheme is. This is when one of the observers measures a continuous variable of one of the modes or part of the quantum system, while the other observers measures discrete variable. So for example, Alice can measure general current detection to quadrature via balancing modality. Can perform on balancing modality while perform detection, analyzing output light with an on-off detector, which may yield only two outcomes, 0 or 1. And in my work, I tackle a question of how do we test Bell non-locality in such scenario? Because when continuous variables are involved, it's quite complex question. No general approach exists to testing Bell non-locality. Additionally, I restrict my attention to the case when each observer may use only two. And this actually resembles the scenario for which CHSH inequalities can be a continuous variable. But a well-known approach is that you can discretize the general quadrature, right? The continuous variable. You can split the set of the real numbers into two subsets and introduce an effective variable, which I label tilde x, which takes two values based on where the real general quadrature is, right? Whether it's inside the red set or whether it's inside the blue set. And the good news is that it was proved by Stefano Pironio that such generalized CHSH inequalities are the only thing that you need to consider in a hybrid scheme to test Bell non-locality. Well, the bad news is that there are infinitely many ways to introduce such an effective variable, since, well, actually this may a bit deceive you because there red set can be much more complex. It can be union of any amount of my work. I concluded that there are actually two ways to discretize the general quadrature, right? And now you can see one of those ways. You have to pick the red set so that each value of x inside there satisfies the inequality that you see on your screens. This is what concerns the general quadrature that corresponds to one of the settings, phi1. For another variable that corresponds to the setting phi2, the way to discretize this variable is on your screens. And actually, I mentioned that there are actually two ways to discretize the general quadrature. The other one is obtained simply by interchanging phi1 and phi2. And this yields inequalities that must be satisfied in order for the state to be local in such hybrid measurement schemes. I know that it doesn't really look like CHSH inequalities. However, if you expand the expressions inside the integrals, it can be seen that there indeed are CHSH inequalities. So this is just some kind of a closed and convenient form for it. I applied such inequalities to well-known states. For example, to most squeezed vacuum does not exhibit non-locality in such hybrid scheme, while cat state, right, whose formula you can see on your screens, actually exhibits non-locality if you pick such a measurement settings value that you see on your screens. Okay, so the results of my work are actually is a development of necessary and sufficient condition for testing Bell non-locality in such hybrid schemes. So thank you for your attention. We'll be glad to answer some questions if you have any.
Thank you very much. Thank you for the very good timing. One question I have is, would it be difficult to do the measurements which somehow detect this or violate these inequalities? Are there technical challenges to that goal?
No challenges, because those measurements that I talked about mainly
the connection is
balance
sorry, Vadym.
Balance yes.
Mm-hmm. Your connection was breaking up.
What?
The connection was breaking up. So maybe if you switch off your webcam, then maybe we can hear you.
Okay, let's. Yes. Can you hear me now?
Yeah.
Yeah. So those measurements that I was talking about are extremely common in quantum optics, and there's really no problem to test experimentally.
Okay, I get it. Thank you very much. Thanks for the nice talk, and thanks for being here. Let's move on to the next speaker. The next speaker is David Pataki, Budapest University of Technology and Economics. David, could you please share your screen? And the title of the talk is Optimal Gate Protocols for Universal Quantum Computation with Crossbar Architectures. It works nicely, so please go ahead.
Thanks. Hello, everyone. I will briefly explain what a crossbar architecture is and how the gate protocols should be optimized. So as you probably know, spin qubits in silicon quantum dots are promising for large-scale quantum processors since they have small characteristic size, long coherence times, high-fidelity universal quantum control, and the capability of high-temperature operation. But one physical limitation of having few thousand or even a million qubits in a single chip is the problem of control lines to achieve full qubit control without a large overhead in the number of wires. Crossbar control architecture was proposed to overcome this issue, and it is basically a grid of quantum dots, which are now loaded with electrons according to this checkerboard pattern. Manipulation of the spins is possible with magnetic fields, and we can also move these qubits. The qubits are indexed with row and column indices, and the charge occupations can be tuned with the diagonal lines controlling the on-site energies. And the tunnel couplings are controlled by the vertical and horizontal lines. In this architecture, with 6,000 control lines, roughly 1 million qubits can be addressed, which is obviously a huge reduction. But in this case, the ability for parallel operation is reduced due to crosstalk effects. Therefore, we simulate single and two qubit gates to compute target qubit fidelity and ideal qubit infidelities. And our aim is to find optimal parameter regimes where the target fidelity is maximal, meanwhile the crosstalk is minimal. One example is the rotation around the z-axis. Consider a qubit with a neighboring quantum dot. If we have an inhomogeneous magnetic field, so this Zeeman splitting is different for the two dots, then the Larmor frequencies will also be different. And if I lower this tunnel barrier between the dots, and I delocalize the electron between the two quantum dots, its spin will feel the Larmor frequency difference, and it will start to precess around the z-axis. And starting from the x eigenstate, if I do this protocol properly, it will result in a pi-z rotation. So here's this targeted red electron, and for this process, I need to lower this tunnel barrier, and I also need to tune these potentials in these crossbars to control the on-site energies. And but this will also affect the state of the ideal qubits in these two columns as well. And so these ideal qubits will suffer a small z rotation during this protocol, and the two nearest neighbors are the most affected. So with fine-tuning, we can perform a high-fidelity Pauli Z gate. However, the ideal qubit infidelity could be also significant. So there is a trade-off between these two quantities. So the take-home message is that using proper optimization, the crossbar architecture is a promising platform for large-scale quantum computers. Thank you.
Thank you, David. Thanks also for keeping the time. We have time for a question. There is no question in the chat or in the Q&A, so I can ask one. What do you think? How far is this from actual realization? So how far is this crossbar architecture from actual realization?
Yeah, good question. So nowadays we are somewhere around 4x4 spin qubit architectures. So I think this is a bit futuristic, but anyways, it's a good concept, and it just needs some time to develop these precision and experimental techniques.
Okay, thanks a lot, and thanks also for the talk.
Thanks.
Let's move on. The next speaker is Onur Pusuluk. Onur, are you ready? Can you please share your slides? So Onur is from Koç University, Turkey. The title of the talk is ThermoCoherent Effect, Generalization of Onsager's Reciprocity Relations for Heat and Quantum Correlations. Please take it away.
Thanks a lot. Can you see my pointer as well?
Yes.
Hi, everyone. Today I will talk about the reciprocal relations between heat and quantum coherence flows and emphasize some possible technological applications. Let's start with thermoelectricity, which is of importance in increasing energy efficiency by turning waste or excessive heat into electricity, and in solid-state refrigeration by running backward. Although it was experimentally discovered by Seebeck and Peltier in the first half of the 1800s, the underlying theory remained immature until Lars Onsager published his famous reciprocal relations between heat and charge in 1931. Onsager's paper built on a paper of Lord Rayleigh, in which he focused for the first time on the whole dynamical process by which a thermodynamic steady state is attained in a gas of particles. And Lord Rayleigh captured the essential physics by developing a simplified collision model, which in turn allowed him to reveal the role of environment's initial conditions, this mass and velocities, in the heat conduction. We followed the footsteps of Lord Rayleigh and Lars Onsager to systematically establish quantum reciprocal relations between heat and quantum coherence, for which we introduced the term ThermoCoherent Effect. And specifically, we constructed a simple and physically insightful quantum collision model for the open system dynamics of a thermometer in a gas of quantum projectiles. And each projectile consists of a pair of locally thermal particles which have a quantum degrees of freedom represented by lambda. And first, we obtained the quantum version of Rayleigh's heat conduction equation and found that quantum coherence represented by this lambda can affect the rate of heat exchange with the thermometer. And then, analogous to Onsager's use of Rayleigh's principle of least dissipation of energy, we used entropy production rate to identify coherence current, and then showed that both coherence and heat flows can be written in this form, which is the quantum version of Onsager relations. In this way, we provided the theoretical basis for some experimental observations indicating that quantum coherence and correlations can cause anomalous heat flows from cold to hot in microscopic systems, like the one reported in this paper just 3 years ago. Additionally, in a collaboration with Özgür Müstecaplıoğlu, we showed that quantum coherence can also prevent heat from flowing between two systems at different temperatures. For example, in this region, you can show that there isn't any net heat current between the two systems, although there is a temperature gradient between them. Similarly, quantum coherence can actuate a heat exchange in the absence of any temperature difference, as in this case, without violating the second law of thermodynamics. And our results and methodology promise thermocoherent analogs of Peltier and Seebeck effect technologies in various platforms. For example, thermocoherent Peltier effect can be exploited to inject quantum coherence into a region to make compact non-thermal cooling or heating environments where injecting heat would be inefficient. Heat transfer in a quantum or nanoscale can be controlled and induced using well-focused coherent lasers. And this may pave the way for a temperature manipulation over different regions within a single molecule. A promising example can be polymerized chain reaction technology, PCR technology. And thermocoherent Seebeck effect may have implication to produce quantum coherence by a thermal gradient. Thermal diodes and transistors can rectify heat flows on the micro and nanoscales. So our findings suggest that these phononic devices may be particularly used in thermocoherent preparation of quantum bits in quantum computers. This possibility may motivate further studies to design quantum technologies based on the phononics rather than electronics. And thermocoherent phenomena also promise improved control over chemical reactions and nanofabrication techniques, or optimization of thermocoherent coefficients can be used to design decoherent materials to preserve coherence in a reservoir. But let me stop at this point to not exceed my time too much, and thank you for your attention.
Thank you very much, Onur. So there are no questions in the chat and also no question in the Q&A. You have mentioned an experimental paper 3 years ago. Could you specify what was the quantum object in that particular experiment?
In this experiment, they used the nuclear spins of carbon and oxygen atoms in a chloroform molecule. The spin states of these two nucleus are the system of interest. They started with an initial discord shared between these two spins, and when this quantum correlation consumed during the heat exchanging interaction between the two spins, they show that heat can flow from cold to hot in this system.
Very interesting. Thank you very much. It's time to go on. Thank you, Onur, for the nice talk. The next talk in the session is from Aron Rozgonyi. Aron is from Eötvös University, Budapest. Aron, could you please start sharing your screen?
Yes.
And Aron will talk about quantum error correction with Faceflip repetition code. Whenever you're ready, please start.
Can you see?
Yes, it works. Yes, it's good.
Then I shall start. Okay,
Yes, you can start.
Yeah. Thank you. In my PhD studies, I focus on quantum error correction, and I theoretically model the Faceflip repetition code. This is not a full code, but it can correct phase-like errors. And I investigate whether an optimal code length exists and what it is in certain quantum architectures. So quantum codes are made to preserve the quantum information stored in quantum bits, but are subjected to quantum noise, hence its lifetime is limited. And our goal is to expand its lifetime via logical encoding. So we are taking many physical qubits to simulate only one error-corrected logical qubit. And my model is depicted in the top figure, where the blue dots represent the data qubits, what are used for redundant encoding of information into specific multi-qubit logical states. And a few extra ancillary qubits are introduced and plugged between the data qubits. They are used in stabilizer measurements, and altogether it represents one logical qubit. So for error detection, stabilizer measurements are performed, and some certain observables are measured that are called stabilizers because their eigenstate is the preferred logical encoded state. To the post-measurement state remains identical even if an error occurs, but then it has a -1 eigenvalue. So measuring with all the stabilizers, we have the output of plus and minus ones, what is called the syndrome of the measurement. And by syndrome extraction, we can detect and identify errors by kind, and we can apply an appropriate recovery operation to reestablish the noise-free state. So I investigate the optimal code length of the repetition code in different quantum devices by considering a realistic noise model, such that the relaxation and dephasing. And these noise processes are characterized by the coherence times T1 and T2 or T2 star. And first I considered perfect gates and measurements and took only one round of error correction. And in the figure, the colors represents the code length of the repetition code, which has the highest fidelity for a given parameter set. And on the axis, the qubit idling time and the coherence time T1 are plotted and normed by this T2 parameter. On the left side of the plot, the relaxation is the dominant noise process, what is less detectable by the Faceflip code. Hence, here it doesn't burst encoding a logical qubit instead of using only one physical qubit. But as we go on the x-axis to the right, the dephasing process is getting more relevant instead of the relaxation. Hence, it's getting more versatile to scale up the number of qubits used in logical encoding. And about this plot, we can conclude it might not be worth building Faceflip code in superconducting architectures, because in such a device, the relaxation is the dominant process, but instead in semiconductor device, it's more reasonable to build that. And furthermore, for given T1 and T2 parameters, we can conclude what is the reasonable length of this Faceflip code. And because of the time constraint, I cannot go further now, but I have some additional results that contains C0 gate noise, measurement noise, and more error correction rounds. And altogether, these results could support the quantum computer engineers by how long quantum code should be built in a device to reach the most optimal error correction. So thank you for the opportunity, and thank you for your attention.
Thank you, Aron, for the nice talk and for keeping the time. I don't see any questions in the chat or in the Q&A. So my question would be about the experiment. So how far ahead are similar experiments with superconducting qubits and spin qubits?
Yes, we have some experiments, but we don't have an existing code yet, because, as I mentioned, this is not a full code, so it can correct only phase errors, but we want to build a full code that corrects every errors, and that's need a more difficult code, like surface code. And for example, the Google, they claims that in 10 years they will have an error corrected computer. Is that an answer?
Yes, it is. So I understand that superconducting qubits, people are using this order of magnitude of qubits, so like 20, 30, 40, 50 within qubits. Do they have similar scale devices, or?
Yes.
Mm-hmm. All right. So I think we should move on. Thank you very much for the talk.
Thank you very much.
And we have two more in this session. The next one is from Hrvoje Skenderovic, Institute of Physics, Zagreb, Croatia. Hrvoje, can you hear us? Can you share your screen? You are muted now. Now we can hear you.
Yeah. Hello,
Yes.
everybody.
Yes.
My name is Hrvoje Skenderovic, coming from Zagreb and Institute of Physics. I hope you can see now my screen. Yes.
Yes, it works.
So the title of the presentation is Phase and Amplitude Reconstruction of Heralded Single Photon Holograms. So in this work, we constructed a source of heralded single photons based on spontaneous parametric down conversion. We measured quantum coherence of the second order of this source, and we got this quite low number, this G2, 0.004. As you know, the theoretical value is 0 for single photons. So with this source of single photons, we started, we wanted to make holographic measurements. And so in doing so, using first photon we used for heralding. That will be, if you look at this scheme on the left, in the left corner. So we send one of the photons to the single photon detector for heralding, and the other photon enters our holographic setup. This is classical holographic setup in image plane configuration with Twyman Green interferometer, which kind of Michelson interferometer. And before this interferometer, we also have two single photon detectors for examining, for checking or testing the state of our photon before and entering the interferometer, and also the recording detector are actually two single photon detectors with after a beam splitter, and they are scanning in the image plane and in order to get a hologram. So we are certain that we have just one photon in the setup, and with this one photon we did holography. Sorry. So these are some results. We had, I present here two objects. One is like some kind of bullseye target, and the other one is microscopic cover glass. On the first column beside the hologram, beside the object, you see the hologram made by non-heralded light, and these holograms are with quite low visibility, but with the same photons, but using heralding procedure, we can get much better holograms. And with these holograms, we are able to reconstruct, to make amplitude reconstruction and phase reconstruction that you can see in the last row. And so this single photon acts as a classic light. We see that it has a frequency in a Fourier spectrum that we filter out and get reconstruction. So that, sorry. That would be actually my last slide. So the conclusion is that we check the state of the photon. We are sure that it's just one single photon, but we can show that with this one single photon acting as a reference photon and object photon at the same time, we can record hologram that can be reconstructed in phase and amplitude space. And that's
Thank you very much.
I can conclude.
Thank you for the nice talk. I might have a question. I'm completely an outsider in this topic, but I was wondering what are the future plans? What are the follow-up steps to this research? What is the visionary goal to reach here?
Well, one direction would be to use this as an application when you need low light detection. But if you see with the low light detection, just using ordinary light, you cannot see hologram, or you can see just vaguely some fringes. But if you use heralding, you can reconstruct much better picture. Of course, the problem is with this is that we're using scanning diode, so that takes some time. But I hope with development of single photon detectors, cameras or arrays, that we can use one of these new devices to get picture much easier or much quicker.
Thank you very much. Thank you for the talk.
Thank you.
And we arrived to the last talk of this session. It will be given by Mikhail Belogolovskii from Kiev Academic University. Mikhail, we are glad that you could be here with us. The title of the talk is New Developments in Josephson Junction Research. Could you please start sharing?
Okay. I can start already. Yes, to wait a little bit when it appears the presentation. Yes. So I would like to present the main result of my collaboration with American colleagues, and I have to say that unfortunately it stopped at the moment from their side. So for me, it seems to me that the results are very important for superconducting electronics, and I would be glad to find partners in Europe, first of all in Eastern Europe. So I'm speaking about Josephson Junction. The Josephson Junction is well known. It is the basic element of the superconducting devices, setups, as classical as quantum. So what is the junction? It consists of two superconducting electrodes with a so-called weak link that can be made of is to realize the situation when we have the difference in quantum phases for the two superconducting electrodes. So if the difference of the quantum phases is 5, here the result is well known that the critical current across such a junction is a sine function of 5. So it's a very unusual electronics device. Nothing similar exists in the classical case, and because of it is actively used in different quantum hardware. So how can we influence the phase difference between two superconducting electrodes? One of the ways is to apply a magnetic field that is parallel to the interfaces. This magnetic field changes the phase difference in all textbooks on superconductivity. It is written the results, and the result is such a dependence of the maximum critical current on the magnetic field. So, or on the magnetic flux across the weak link divided the two superconductors. So the formula is written here, and in each textbook there is written that to prove that you are really dealing with a Josephson junction, you should measure the dependence of the maximum supercurrent across the junction as a function of the magnetic field, and you should obtain such a curve that we name it Fraunhofer pattern, since it is similar to the same, to the related curve in optics. Another important superconducting device is screed. Screed consists of two Josephson junctions coupled by a superconducting loop. Because of the interference in two arms of the superconducting loop, the resulting dependence of the maximum critical current is not such as for a single Josephson junction, but it is a periodic function. So it is a cosine function of the magnetic flux or across this region or the magnetic field as you want. Yes, it is better for practical purposes, and it is well known that now screed is a gold standard for all precise measurements of the magnetic field. So all was known before this experiments activities with American colleagues. What was done in the USA? For the first time was measured such two structures. So we have two superconducting electrodes and 10 bilayers formed by nanometer thin normal interlayer and ferromagnetic. So there is such a periodic structure that consists of 20 layers with a thickness from 1 to 3 nanometers, formed by a normal metal and a ferromagnetic one. And in some such devices, there was also an insulating interlayer, as in classical Josephson junctions. So, suddenly in both cases, we observed not a Fraunhofer pattern as we expected. This is the red curve is a Fraunhofer pattern measured with the same electrodes, but only a single insulating interlayer, but such a periodic structure, so that we name screed-like. So it is the first case when in such a complicated structure we have observed not a traditional characteristic of the maximum superconductor versus magnetic field, by the periodic structure. And the weak link is built from traditional trivial methods. So we have an explanation, and it was published in Physics Applied, but we are not satisfied with it. So what we explain is the difference between we argue using the difference of the quantum interference in the center of such structure and near the edge. So in our explanation, we have something like a skid. So the main supercurrent is going across the edge states, but in the center it is suppressed by the chaotic structure of this weak link. And so we have something like a squid, and because of this we have such a periodic structure. My feeling is that maybe it is not so usual, but maybe we are dealing with something new topologically protected edge currents. But for this to state it, we need new experiments. So my task was to tell about some very exciting, from my viewpoint, results for new types of Josephson junctions with such a multi-layered structure inside them, and to propose possible maybe somebody could join this activity for future.
Thank you very much, Mikhail. Well, there is one question in the chat. The previous diagram, is that a transistor diagram? Maybe somebody from an electronics background is asking this.
Is it transistor or not?
Is it a transistor diagram? Yes.
No. It has no relation to transistor. It is a usual two-electrode junction and Josephson junction, and the new aspect is only the presence of such multi-layer structure inside and the squid-like dependence, which proves in our opinion that the current is going not across the whole cross-section, but only at the edge of this device.
Clear. Thank you very much, Mikhail. Thank you for being here, and thank you for a nice talk. This concludes this session of lightning talks, and we are just about to move on to the last lightning talk session with the 8 remaining talks. So see you there, over there in the other session. Goodbye.
Goodbye.